Um, uh, Good morning, good afternoon, good evening, good night, wherever you are. So I'm I A Krishnamurthy. I'll be chatting this session on SPM, SMI, and FAC posters. And Aditya Balu, who is my postdoc, he'll be chatting the session in the morning, just as backup if I don't get up in the morning. Anyways, just to introduce, I think we got a bunch of very good submissions for posters this year. 6 posters were finally selected, and the 3 posters will be presented during this session, and 3 more will be presented in the session at 6 hours from now. Essentially, we'll have 5 minutes per poster for a lightning talk, and then we'll have some more time, about 5 minutes for discussion and questions. And as you all know, you can also look at the Discord channel if you want to interact with the authors on a one-on-one basis. With that, I will start transfer control to the first presenter, Joy Ajay, and she'll be talking about optimization for topology optimization, essentially topology optimization.
Okay, let's start. Okay. Hello everyone, I'm Xiaoya. Today I'm going to be talking about our new work that the alternating optimization algorithm of stress-based topology optimization. Here I will give a brief introduction to our problem. Stress-based topology optimization is a very important branch of structure design. It has been widely used in various fields such as 3D printing and so on. L-shaped beam structure is a benchmark structure in the field of structure design. If we input the L shape like this, and act the force on the right top corner. Without considering the stress, maximum stress, the optimized layout is shown like this. We can observe that there is one stress concentration here that will lead to the structure failure. So our problem also we focus on the question how to effectively incorporate stress constraints in topology optimization. There are 3 challenges here in the field of the stress-based problems that are singularity problems, the local nature of stress constraints, and the highly nonlinear problem. There are some approaches to alleviate the previous 2 problems, and you can refer to the reference in the slides and for more details. Our work focus on the last problems. In other words, we want to reformulate the stress-based model and avoid the highly nonlinear problem. This is the general formulation of the stress-based problem. We state as a model Q. We take the compliance and the objective function and restrict the model by the volume constraints and the stress constraints. Here, sigma E stands for the van Mises stress of the element E, and sigma star is the maximum allowable stress. This model is non-linear and non-convex. In our method, we first introduced a new set of stress variable alpha. And this new variable alpha stands for the van Mises stress on every element. So we formulate the model Q into the model Q0. The stress constraints can be separated into 2 constraints, that is constraint 3 and constraint 4. To solve the model Q0, we first input the stress constraints into the objective function by augmented Lagrangians and set the rest constraints to the constraints. So we can get the model Q1. And then we update, and then we adopt the alternating direction optimization algorithm by continue updating the density, the stress, and the Lagrangian multipliers in turn. Here I give the result of the L-shaped beam. Without stress constraints, we can observe the one stress constraint here, and that's region we don't want to print in the real work. And with stress constraints, one stress constraint, after adding the stress constraints, the maximum stress is 0.5. But before, without stress constraints is 0.35, and the corner of the final layout is smaller than before. In this slide, we show the iteration process. We plot the complex convergence process by 6 different solvers. The first row is the result from the model Q0, and the second row is the result from the model Q1. The result from model Q1 is smaller than is from Q0. That means the reformulation takes effect. So I'd like to conclude today's presentation by summarizing into 3 points. First of all, a dual variable formulation is introduced here. After that, an alternating direction optimization algorithm is proposed to seek a better local optimal solution. At last, the numerical suggests that this new formulation is better than before. That is, the result is up to 25 smaller than that from the conventional formulation. Okay, that's all for my presentation.
Awesome, thank you. Are there any questions from the audience? You can either type in or ask or unmute yourself and ask. While you're waiting, I had one question. So you noticed that the corners were rounded when you did this. Do you think you can control this roundness by changing the weights for the two? Right now, I assume it's equal weights for both the stress and the density.
You mean I restrict the model is based the density. Is density-based topology optimization. You mean I can restrict the density by small here? Okay.
No, I was meaning like if you go back to the formulation slide, one slide back, after this, sorry. Okay. The alternate formulation that you are doing.
This is our formulation.
Yeah. So here, the Lagrange multiplier, you just have equal weights for both, right? In the sense that the density and the stress have the same 50%, 50% weight. But if you give more weight for the one versus other, you'd probably get a better or a more rounded solution, and you can control it better.
You mean to control the corner, the smaller of the corner?
Yeah.
Yes, if we don't want to the region of the stress concentration, the corner of the L shape must be smooth. If it didn't smooth, it should be a stress concentration here, and we stress the alpha and the sigma delta here. That's be very large, and that didn't satisfy this objective function. And
okay, yeah, that's right. Okay. Makes sense. So I had a question from Tim. Does changing the sigma also change the bend in the final optimization shape?
The final optimization? In which case?
So the bend that you see between between the B and D in this figure that you are showing?
Yes, the A is the input strip, and the B is without stress constraints without considering the stress constraints, the layout or the optimized layout. And the C is the result from our method, and the D is the stress distribution of our method. Yeah.
Right. The question is whether that
the
bend changes on sigma. So that you see the whether I can highlight it. I don't know.
Yes, the maximum of the final structure is 0.5, but before is 0.35.
Okay.
Yes, I restrict the maximum allowable stress is 0.5.
Okay. Sounds good. Any other questions? All right. Thanks, Joy. Now we'll go to the second talk, which is by Jun Wu, and he'll be talking on fabrication sequence optimization for multi-axis additive manufacturing.
All right, thank you for the introduction.
Yeah.
I'm presenting this work on behalf of my co-authors, Weiming Wang and Fred van Kolen. And the title of this work is Fabrication Sequence Optimization for Minimizing Distortion in Multi-Axis Additive Manufacturing. We are interested in wire and arc additive manufacturing. It uses metal wires as feedstock and arc welding tools as an energy source. It is a suitable candidate for fabricating large metallic components in aerospace and maritime industry. The components are of the size of a meter to several meters. One of the problems with WAM is that it results in very high residual stress and distortion of the fabricated component. This is due to very high temperature gradient and phase transition involved in this directed energy deposition process. So if we look at the bottom right corner, this regular two-layer component has a distortion of 40 millimeter, which is huge. This animation compares the fabrication of an L-shaped component by using the standard horizontal plane layers on the left side and using curved layers that are optimized by our algorithm. So it confirms that fabrication sequence represented by these layers has a huge influence on the final distortion. And this work is motivated by recent advances in robotic fabrication. It has been demonstrated that by using robotic platform, it allows to fabricate or accumulate material along curved layers. So we ask ourselves, can we make use of these curved layers? And we try to find the best decomposition of curved layers into a sequence that could minimize the final distortion. For this purpose, we first have to develop a method to predict the distortion given a fabrication sequence. So here we look at distortion from a macroscope perspective. Suppose we deposit a liquid square without interaction with the embedded material. This liquid will shrink as it solidifies from liquid to solid. So the volume is reduced. However, if this contraction is restricted by a build plate or by a part that has already been solidified, then the contraction is restricted. That introduces residual stress on the interface between the layer and the build plate, or the layer and the previous layer. And consequently, the distortion becomes anisotropic. So for instance, here, the top part shrinks larger and also the height is reduced. And if we simulate this process progressively, we can evaluate the distortion of the entire component shown in this animation. We develop an optimization method to optimize the sequence. So we introduce a time field to encode the fabrication sequence. The time field is normalized between 0 and 1. So each point in a design space carries one of the design variables. 0 means it is at the beginning of the fabrication. 1 means this element is fabricated at the last of the fabrication. Given a continuous time field, it could be segmented into a prescribed number of layers. This L shape, for instance, it is supposed to be fabricated in 8 layers. So we segment it by 1/8 as an increment. The equation shows the formulation. We minimize the amount of distortion measured by the displacement of the nodes in the domain. The physical meaning of this distortion will become clear in the next slides. And there are a few restrictions or constraints. The first set of constraints is related to the linear equilibrium equation of elasticity. So here, F is the equivalent thermal distortion force, and the delta U is the increment in the displacement due to the addition of a particular new layer. So we have 8 layers. So for each additional layer, we have one of this equation. The second constraint restricts the design variable to between 0 and 1. So we have a continuous design variable. And the last 2 constraints are related to the manufacturability. Here we consider 2 essential manufacturability constraints. The first one is about the deposition rate. So we assume the deposition has a constant rate. It is necessary to impose a constraint on deposition rate because without a deposition rate constraint, the optimization would suggest you to fabricate this component in one shot. So there would be no process, so no process dependent distortion. The meaning of the last constraint is related to manufacturing continuity. Physically, it means each new layer has to be attached or be adjacent to one of the previous layers. So it is supported. This supporting shouldn't be confused with self-supporting angle in additive manufacturing here. Supporting means it is connected to one of the previous layers. So if we solve these equations by gradient-based optimization algorithms, and here it shows some of the results. So if we can measure the distortion of a particular node, or we minimize or we maintain the flatness of an edge measured by the relative distance between 2 nodes in the middle. And we could also maintain an angle formed by a few nodes shown on the right-hand side. As you can see in all these cases, the fabrication sequence adapts to the particular objective, and numerically, the distortion measure is in the order of 10 to the power of -3 compared to the unit size of an element of 1. So the distortion is very small. And this is achieved because we have a large number of design variables. So in this design space, it is 40 times 60. So we have a few thousand design variables leading to a different sequence shown on the bottom. We have also tested this algorithm by on 3D complex geometry. It also works pretty well. To conclude, we have demonstrated that fabrication sequence has a huge influence on the amount of distortion in this additive manufacturing process, and we can effectively reduce distortion by using optimized layers that are curved. As future work, we are particularly interested in experimental validation of the optimization framework. As a first step, we would like to calibrate this initial stream model, relate this initial stream to the manufacturing parameters. There are also many other manufacturability constraints, for instance, the residual stress, and we would like to integrate it into the optimization framework as well. Thank you for your attention.
Thanks, Jun. I think that was an interesting talk. If anyone has any questions, please chat, put it on the chat or ask. I had one question here. Is there a constraint on the layers to be 8 layers, or you can have any number of layers that you want? Just an example that you showed here.
In the examples, I have 8 layers, and this number of layers is prescribed. We could also prescribe 10 layers, 20 layers. That's not a problem. And the relevance is with a different prescribed number, the number of equations in the formulation is increased. The maximum we have tested is like 20 or 30 layers.
Oh.
Okay, I saw the question. Can you print in a different number of layers than what you optimized for? Can you print it in a different number of layers than what you are optimized for? From all our results, if we prescribe 8 layers, it is fabricated in 8 steps. This is because in our formulation, we prescribe the deposition rate. So 1 layer only fabricates a portion of the entire component. If we allow this deposition rate to be higher than 1/8, I think we will be able to achieve a result with only 6 or 7 layers. Depends on the amount of material that is allowed to be deposited in each layer. Yeah.
Thank you. Any other questions? All right, thanks, John. So we'll now go on to the final presenter for the session.
Thank you.
Thanks. Yeah, Martin Skrotsky, and he'll be talking about a large-scale evaluation of neighborhood weights and sizes. And so, as you can see, the first 2 talks were on fabrication. We are now going to the shape modeling kind of posters now.
Yeah, thank you for the nice introduction. I see that the next session starts in 4 minutes, so I try to make this quick and give you the opportunity of listening in here and still making the next session. So I'm going to report on some joint work with Erik Zimmermann here. And this is mostly motivated by actually statements we've heard at this conference also. Whenever people are modeling something, whenever algorithms come into play, what people do is just fix a number of neighbors. Let it be of triangles and meshes, or let it be in points where it's usually the k nearest neighbors. And people tend to fix one magic number, k equals 6, 10, 24, whatever. And in this work, we meant to evaluate this choice and see whether it's actually motivated by the outcomes or whether this could even be optimized. So our setup consists of a point set P in this case, but really you could apply this to any other setup of geometry with normals and some neighborhoods. And what we're going to focus on here is the scalar product of the normals. So we want to evaluate a bilateral weighting on these points where not only the distance to the point, but also the normal similarity comes in. We're going to do this by evaluating the sigmoid function, which basically has 2 parameters, A and B, where A tells you how similar 2 normals have to be taken into account in the first place, and B tells you how steep the increase of this sigmoid is, right? So for an infinitely high increase, you basically have a sharp cutoff of everything that's too dissimilar. If you have a rather low B, you take into account dissimilar points, but maybe not, with not so high of a weight. So we have this weighting. Now we're going to evaluate these, and we're going to turn to the covariance matrix of each single neighborhood. And on this covariance matrix, we can determine its eigenvalues, which give rise to these 3 quantities, one measuring basically the linearity, the planarity, and the scattering of this particular neighborhood. So how well does this neighborhood reflect this given surface structure? And for each of these quantities, we can evaluate a Shannon type error, giving us an idea of how well this neighborhood captures the local surface. So what we're going to do is we're going to evaluate it over a pretty broad range of different neighborhood sizes K that we took from different papers in the literature where they seem to be very well used. And we're going to evaluate them on our weighting scheme. And remember, we had 2 parameters there. So for each of these K, we're going to find an optimal parameter pair, A star and B star. All right. Oh yeah, right. I should tell you, we run this on more than 1,000 clean meshes and 9 large-scale noisy models. That is because we find that most of the papers out there, when they present their algorithms, what they do is they're going to present you like 3 or 4 models. So we really wanted to know, is this something that works out in the general scheme of things? So what we found here is that if we go to the clean models, we do find that optimal weighting is with very high values of A, so neglecting a lot of points that have dissimilar normals, making a sharp cut here, but very low values of B, right? So even if you do cut as many points as possible with dissimilar normal, you still want to guide, have the others guide your process in a way with smaller or lower weighting terms. For the noisy models, that was quite interesting to us. We found that you cannot so much cut points, and that is simply because you need to take into account larger neighborhoods to have meaningful values in the first place, and that is clearly due to the noise. So far, maybe not so surprising. You want a large A parameter, as large as possible, to still have meaningful values, but discard dissimilar points. And you don't want these equal weights or sharp cutoff weights that are usually used in the literature, but really some weights in between. Regarding the neighborhood size, what we found is that for the clean models, it's really feasible to have a very small neighborhood size. But for the noisy models, we really needed a wide distribution of neighborhood sizes in order to capture the optimal effects here. So please, whenever you set up an algorithm, don't use a fixed K, but use a varying neighborhood size. And that's all I meant to say. Everything else is in the paper. Please find me in the Discord or ask questions here. Thank you so much.
Awesome. Thanks, Martin. Are there any questions for Martin? Looks like there are no questions. Since we are probably eating into the other session's time, in the interest of time, I'll ask if anyone have questions for Martin. Please go ahead to the Discord channel and ask your questions, and we can have a viable discussion going on. We'll have the second part of the poster session in about 5.5 hours, and we'll have 3 more posters for the last part. Hopefully, I'll see you all there. Thanks very much, and have a good rest of the conference.
Thank you for organizing.
Yes, no problem. All right.